Hello there.
Welcome to my YouTube channel. Don't forget to like, comment, and subscribe. That's how you do YouTube, right? Um, all right. Well, anyway, today we're going to learn about Prim's algorithm. So Prim's algorithm is a greedy algorithm that traverses through a weighted connected graph and finds a minimum spanning tree. The minimum spanning tree will connect all vertices in the graph while refraining from producing a cycle or being acyclic. This algorithm can be used for many things, primarily related to networks, including communication, computer, transportation, and electrical networks. When performing Prim's algorithm, if you use a priority queue array on the weighted graph, this results in an efficiency class of big theta of v squared, or the number of vertices squared. However, using a minimum heap with the weighted graph results in an efficiency class of big O of e log v, or the number of edges times the log of the number of vertices. So let's view an example. So here on my iPad, I have a graph. It is a weighted connected graph, and we're going to keep track of two solution sets. These will be VT, which will hold our vertices, and ET, which will hold our edges. So the first thing we need to do with Prim's algorithm is simply start at any arbitrary vertex. It doesn't matter which one because, like stated, it is a connected graph. Therefore, they will all reach every single one no matter what. So let's just start with A. So I'm going to highlight A here, and then I will add A to our set of vertices. And right now, our solution set, ET, is empty. So the first thing to do after selecting that initial arbitrary vertex to start at is you want to go to the next edge connected to that vertex with the lowest cost. In our case, we have three edges going from A to C with a weight of 3, A to D with a weight of 2, and A to B with a weight of 7. Because we can tell that A to D with a weight of 2 is our lowest edge, we will highlight that. Highlight the vertex D, and we will add both of those to our two solution sets. So adding the vertex, we just add the vertex. And then adding that first edge, we have A to D with a weight of 2. So continuing here, we just do that same process over and over again throughout the entire algorithm. So our next step, we look at the edges connecting to our selected vertices already. So we have A to E with a weight of 3, D to G with a weight of 8, A to B with a weight of 7, and D to B with a weight of 1. Much like before, we're looking for that lowest cost. So our next lowest cost is in fact D to B with a weight of 1. So we will highlight that edge and that vertex and add both of those to our solution sets as so. So we add that vertex B and we add that edge D to B with a weight of 1. Continuing on in the process, we now have A to E with a weight of 3, D to G with a weight of 8, D to F with a weight of 4, and B to C with a weight of 9. We do not consider edge A to B with a weight of 7 because A and B are both included in our set of vertices. If we were to include this edge, we would create a cycle and therefore not create a minimum spanning tree. So our next smallest one is in fact A to E with a cost of 3. So we will go ahead and highlight that edge and select that vertex. Add both of those to our solution set as so. And continue on with our iterations. So next up we have E to G with a weight of 1, E to F with a weight of 4, D to F with a weight of 4, and B to C with a weight of 9. Our next smallest is in fact E to G with a weight of 1. So like before, we will select those two and we will add our vertex G to our set of vertices and the edge E to G with a weight of 1 to our solution set of edges. Moving on, doing the same thing, we have G to H with a weight of 6, E to F with a weight of 4, D to F with a weight of 4, and B to C with a weight of 9. As we can tell, our lowest weight is 4, though we have two edges that contain this weight. They both lead to F, they both weigh 4, so in this case, it really doesn't matter which one we select. So for our sake, I'm going to select edge E to F. That will connect to F, and that has that weight of 4. So then we go ahead and add both of those to our solution. So we add the vertex F, and we add that edge E to F with a weight of 4. We continue on, much like before. So now we have B to C with a weight of 9, F to C with a weight of 10, F to H with a weight of 5, and G to H with a weight of 6. Our lowest is, in fact, F to H with a weight of 5. So we will go ahead and select that vertex, and add both of those to our solution sets. We add that vertex H, add the edge, F to H with a weight of 5, and we continue on. So now we only have one vertex remaining. This vertex is C, and it has 3 edges that lead up to it. So we have B to C with a weight of 9, F to C with a weight of 10, and H to C with a weight of 3. H to C with a weight of 3 is our lowest edge, so we will go ahead and add that after highlighting that. So we have that edge, that vertex, and we add both of those to our solution set. So H, C, 3. Now, when we finish the algorithm, a way we can check to see if we have in fact completed all of it is we look at our solution set. Our solution set should contain edges equal to the number of vertices minus 1. So in our case, we have 1, 2, 3, 4, 5, 6, 7, 8 vertices. So just to write that out, V equals 8, our number of vertices. And we look at our solution set. We have 1, 2, 3, 4, 5, 6, 7 edges. So E of T equals 7. Let's make that E of T. So E of T equals V minus 1, which is equal to 8 minus 1, which equals 7. And so that is correct. We do in fact have all of them as a simple check. So Prim's algorithm is complete. So this right here is our set of vertices, and then this right here is our solution set, which contains the 7 edges and their costs in the order in which we can traverse from A all the way to the end of the graph while still maintaining that lowest cost. So it really is that simple. Prim's algorithm is a very easy algorithm to execute as well as to follow along with, and that is all. So thank you so much for watching, and remember one thing.
May the Fourth be with you.
May the Fourth be with us all.